Okay, let's start doing the next problem. Find the Fourier transform of the signal x of t equal to t e to the power at e of t. Listen, when such a question comes, actually this is a lottery for you students, because you can claim that Fourier transform of this signal does not exist. In simpler way, in simpler talks, we can say that t e raised to at of t does not have any Fourier transform because it obeys Dirichlet condition as t into e raised to at u of t. If you integrate it from minus infinity to infinity, this signal e raised to at is an unbounded signal, and this integral will give you infinity. So this signal is not absolutely integrable, and the Dirichlet condition gets violated. Therefore, Fourier transform does not exist. But you know, we should not do like that. We will assume that we have to obtain an answer, right? So we will assume that this a is less than 0. Okay, so we assume that this a is less than 0. So now the integral exists, absolutely integrable. The signal becomes, and Fourier transform exists. Okay. Now that we have assumed that a is negative, we can start finding the Fourier transform of the signal. Okay, so we can do this in two methods. One is, we can start from the scratch, apply the definition of Fourier transform and find out the Fourier transform of t raised to at of t. Or else we can make use of the properties of Fourier transform. Anyway, let us start from the scratch. Okay, let me make use of the Fourier transform equation to find out the Fourier transform of x of t equal to t raised to at of t. Okay, so what is, assuming a less than 0, what is the Fourier transform of x of t? It is given by x of j omega equal to integral over minus infinity to plus infinity x of t into e raised to minus j omega t dt. Okay, but here x of t is t into e raised to at into u of t. You can see u of t here. So whenever you multiply this whole signal with u of t, you don't have to integrate all the way from minus infinity to plus infinity. Instead you need only to integrate from 0 to infinity. You may be clear with that. After all, doing all these problems, you may be very clear about that. So now x of t is t into e raised to at. Now you don't need to write u of t again, because the effect of u of t has been obtained by or occurred by truncating the signal integral from 0 to infinity. Okay, t into e raised to at into now x of t is over. Okay, now e raised to minus j omega t is left, so I can write e raised to minus j omega t dt. All right, so that is equal to, I can write 0 to infinity t into, I can club this exponential together, so e raised to a minus j omega into t dt. Or we have assumed that a is less than 0. A is less than 0, otherwise we cannot proceed with this problem. So a is less than 0, so I can put minus a here, right? Since we have assumed that a is less than 0, I am putting minus a there. Okay, so I can rewrite this as integral 0 to infinity t into e raised to minus of a plus j omega into t dt. Okay, so I can now integrate it as, this is an algebraic term into exponential term. So first function into integral of the second function, okay, minus integral of derivative of first function. Derivative of first function t is 1. Okay, 1 into again integral of the second function exponential. So e raised to minus a plus j omega into t by minus of a plus j omega. And I can put the limits in the final step. Okay, so this is equal to minus 1 by a plus j omega into t e raised to minus of a plus j omega into t plus 1 by a plus j omega into, now I have to integrate e raised to minus a plus j omega t again. So that will give you e raised to minus a plus j omega into t divided by again one more minus of a plus j omega. Okay, now the whole thing is within the limits 0 to infinity. Okay, so what happens when you put down the upper limit infinity here? It becomes no, okay, infinity when putting here will give e raised to minus infinity, and this whole term becomes 0. So 0 minus, now I am giving 0 lower limit in this equation, I mean this term. So again it is rendering you 0 because t into 0 into something is 0. Okay, plus now you know, now in the second term, in this term I am going to put down the upper limits and lower limit. So that becomes 1 by a plus j omega into, what about the upper limit? If you put infinity here, it's gonna be e raised to minus infinity, that will give you 0. Okay, minus, and now put the lower limit, it becomes e raised to 0 is 1, but you have a denominator here, so it is minus okay, 1 by minus of a plus j omega. Okay, so this is going to be 0, and minus minus gives you plus, right? So the answer is plus 1 by a plus j omega the whole square. Okay, so this is one method of solving this problem, finding the Fourier transform. Or else I can give you another method by applying the properties of Fourier transform. By the properties, you know, e raised to at, it is a standard, e raised to at u of t, e raised to at into u of t is a standard Fourier transform that will give you 1 by a plus j omega as the Fourier transform. Okay, now what happens when t into e raised to at u of t, I'm assuming a is negative. Okay, so what happens when t into e raised to at u of t is taken the Fourier transform? You know, if x of t and x of omega are Fourier transform pairs, then t into x of t, or I can say minus j into t into x of t will be having a Fourier transform d by d omega of x of omega. Okay, so I have to find t e raised to at u of t, the Fourier transform of that. Before that I'm finding minus j into t into e raised to at u of t. Instead of x of t, I'm writing e raised to at u of t. That will be having a Fourier transform d by d omega of x of j omega. If this is x of t, then what is x of omega? Here it is 1 by a plus j omega. So d by d omega of 1 by a plus j omega, that will give you minus 1 by a plus j omega the whole square into, it's not over, into the derivative of the denominator. That becomes 0 plus j. So into j. Okay, so that is the Fourier transform of what? Minus j into t into e raised to at u of t. But what we need is just t into e raised to at u of t. So as per linearity property, we can take this minus j to the other side. So therefore the final answer is t into e raised to at u of t will be having a Fourier transform. This j comes to the denominator in the RHS. So minus 1 by j into minus j by a plus j omega the whole square, which you can cancel, and ultimately the answer is 1 by a plus j omega the whole square, which is again the same result we had obtained using the basic definitions. Okay, we will see the next question. State and prove the sampling theorem for low-pass signals. We have already seen this question in some previous videos, so I'm not going to waste much time on this. So I will just state this sampling theorem and the proof. I recommend you to watch some previous videos of pros and experts, and you will get the idea and proof very elaborately in the playlist. Okay, so the statement of sampling theorem states gives us that a band limited signal can be sampled at a sampling frequency fs and can be reconstructed faithfully from its samples if and only if the sampling frequency is greater than or at least equal to 2 times the maximum message frequency. Okay, so this is a sampling theorem. So what you have to take care is that sampling theorem does not say about sampling alone, but the main part, sampling is not a big deal. We can sample any signal at any time, no need of any criterion, but the reconstruction matters. The reconstruction is the main thing we have to notice. Okay, so a signal can be sampled, but it can also be reconstructed faithfully from the samples only if the sampling frequency is greater than or at least 2 times fm, where fm is the maximum message signal frequency. Okay, so we have already seen this. If this is the message signal frequency band limited with a maximum fm, okay, this is the Fourier spectrum of a message signal m of f. Then what happens after sampling? After sampling, you can see the spectrum of the message signal repeats. The replica of this message signal spectrum repeats infinitely on both sides of the axis. And the repetition frequency that is given by the sampling frequency fs. Okay, so how this comes, the proof and all we have already discussed, so please find those videos in the playlist. Okay, let's jump on to the next question. A continuous time LTI system is described by a differential equation given using Fourier transform. Find the output y of t given x of t e raised to minus t e of t. Okay, so this is a very simple question, but the only thing you have to make note is the question asked is using Fourier transform. Naturally, when we see a differential equation, we have an intuition to move forward with Laplace transforms, and that is easier. Okay, that's easier also, but the question is Fourier transform. So if you are careless while reading the question, you may lose marks, because if you are asked to do it in Fourier transform, you have to do it in Fourier transform and not in Laplace transform. Okay, so let's do this in Fourier transform. So the first step is, as usual, you take the Fourier transform on both sides of the differential equation. You have this differential equation here. Okay, you take the Fourier transform on both sides. So what is the Fourier transform of d by dt of y of t? It is j omega into y of j omega. I can write taking Fourier transform on both sides of the differential equation, and you will get the first term. When you do it on the first term, it is j omega into y of j omega. That clearly results from the time differentiation property of Fourier transform. Okay, plus 2y of t. That is a straightforward thing. 2y of j omega. Y of t will be having a Fourier transform y of j omega equal to RHS. You have x of t alone, so its transform will be x of j omega. Okay, now I can take y of j omega common from the LHS, which will give you j omega plus 2. Y of j omega into j omega plus 2 equal to x of j omega. Okay, now x of t is given in time domain. X of t is given as x of t equal to e to the power minus t u of t. So what is x of j omega? It is a standard result, right? E raised to minus at u of t will be having 1 by a plus j omega as the Fourier transform. So similarly, using this x of j omega, I can write it as 1 by 1 plus j omega because a is 1 here. Alright, so x of j omega equal to 1 by 1 plus j omega. So I can substitute that value here. That implies y of j omega is equal to x of j omega is 1 by 1 plus j omega into this j omega plus 2 will go down. Okay, so 1 by 2 plus j omega. Okay, now what we have to find is y of t in the question. Y of t, not y of j omega, y of t. How will you find out y of t? If you are given y of j omega in the frequency domain, just take the inverse transform. Okay, so in order to find out the inverse transform very conveniently, what we make use is the partial fraction expansion. So I can write it as a by 1 plus j omega plus b by 2 plus j omega. Okay, so we can either we can find the LCM, compare the coefficients and arrive at a and b, or we can do any of the simplest methods to get a and b. I can take a as a is equal to, or I can write it as I can replace a as, how will you replace a? It is very simple. Just I'm going to write the constant here, right, over this denominator, and what value of j omega, you have to take j omega as a variable. If at all it was a Laplace transform, s is equal to j omega. Okay, so you imagine that you are replacing j omega by s, so s is a variable here, right? So what value of j omega or what value of s, in this case j omega, what value of j omega will render this term to infinity? In this j omega equal to minus 1. So what you have to do is you neglect this same 1 plus j omega and put j omega equal to minus 1 in this factor. Okay, so that will be your a there. So what will you get? Putting this, neglecting this factor, because this is same as this factor, and when you put j omega equal to minus 1 here, this transfer function goes to infinity, so you cannot do that. So you neglect the same factor and consider all other factors. In this case there is only one factor left, and put j omega equal to minus 1. Why minus 1? Minus 1 is the value of j omega that turns this denominator into 0. Okay, so what I will get is a is putting j omega equal to minus 1 here, 1 by 2 minus 1 is 1. So a is simply 1. I don't have to find LCM, I don't have to compare the coefficients, form equations, solve them. This is very simple. Okay, similarly what I can do is now have to find b. What is b? You just find out what value of j omega will leave this denominator to 0. It is j omega equal to minus 2. Okay, then put j omega equal to minus 2 in the main transfer function, neglecting the same factor 2 plus j omega. Okay, so the only other left part is 1 by 1 plus j omega. So put j omega equal to minus 2 here. You will get 1 by 1 minus 2 is minus 1. Okay, so minus 1 here. Okay, now this term and this term both are in the form of known or standard Fourier transforms. So it's very simple to find out y of t. Y of t is the inverse Fourier transform of these two terms, and the first term will give you, the inverse transform will give you e raised to minus t u of t, minus second term will give you e raised to minus 2t u of t. So that becomes the final answer of this question. Alright, let's try the next problem. A signal is given by x of t equal to 2 cos 400 pi t plus 6 cos 640 pi t. What is the minimum sampling frequency required to avoid aliasing? If the signal is ideally sampled with sampling frequency of 500 Hz, what are the frequency components present at the output? So this is a 6 marks question. First, let us check what the given signal is. It is x of t equal to 2 cos 400 pi t plus 6 cos 640 pi t. And the first question is, what is the minimum sampling frequency required to avoid aliasing? So that means they are asking about the Nyquist frequency. Nyquist frequency is the minimum sampling frequency that can be used to stop aliasing or to recover the signal. Okay, so we know that theoretically this Nyquist frequency or the minimum sampling frequency required to avoid aliasing is given by fs equal to 2fm. Sampling frequency will be equal to 2fm, where fm is the maximum frequency component of the signal to be sampled, or of the message signal. Okay, so in order to get f of s, what you need is just to find out fm, multiply it by 2 and you will get fs. Okay, so let us see what is fm by the frequency spectrum, for a spectrum of x of t, because x of t is having multiple frequencies. Although it is a cosine signal, it is having 2 frequencies. Okay, so if at all I am marking all the calibrations in f, frequency f, and not in omega, so what is the frequency component in the first term, cos 400 pi t? You know, 400 pi is omega, so what is frequency? Omega by 2 pi. So you take 400 pi and divide it by 2 pi, so the result is 200 hertz. So at 200 hertz, let f is in hertz, at 200 hertz we have got an impulse here. Okay, right? I'm not going to write the amplitude of this impulse, because in this particular question, it is not significant. Okay, now let us see the second term. What is the frequency of this second term? Frequency in hertz. You know, omega is 640 pi, so frequency will be 320. Okay, 320 hertz. So at 320 hertz we can see another impulse. Okay, so similarly in a mirror image, sense, you can see at minus 200 hertz and at minus 300 hertz you can see the mirror images of these components. Okay, now this is the x of f, Fourier transform of x of t. Now what is the maximum frequency component of the message signal? No doubt it is 320 hertz. Okay, this component is the maximum frequency component and it occurs at 320 hertz. That means our fm is 320 hertz. Okay, fm is equal to 320 hertz. Therefore, what is Nyquist criterion? fs is equal to, at least will be equal to 2 into fm, which will be 2 into 320 hertz, equal to 640 hertz. So this is the Nyquist frequency, or the frequency required just to avoid aliasing. Okay, now they have asked one more question. If the signal is ideally sampled with the sampling frequency of 500 hertz, okay, so they are changing the question criterion. They are sampling with 500 hertz. Okay, then what are the frequency components present at the output? Okay, so for that I can redraw the sampled signal spectrum. I mean spectrum of the sampled signal. Okay, so I'm going to draw the x del of f. What is x del of f? It is the Fourier transform of the sampled signal. Okay, in the previous the first part of this question we have seen the Fourier transform of the message signal, but now we are going to draw the Fourier transform of the sampled signal. So what is the peculiarity of the Fourier spectrum of the sampled signal? It is nothing but we can see the message spectrum as such, okay, message spectrum as such, but replicating infinitely to the either side of the spectrum. Okay, so this is the message spectrum, but it is going to be replicated. It's going to be replicated, infinitely to both side of the spectrum. So same thing is being replicated. Okay, whatever this was the original signal spectrum, this is replicated one time here and many times to both sides. Okay, so I can represent some of the components. Okay, it goes to infinity here, right? Similarly, we can see replication in the negative side also, negative frequency axis also. Okay, right, like this. Now, what is the so this is FM we have already got as 320 hertz. It's the maximum frequency. Here it is minus 320. Okay, now what will be this frequency, the frequency over here? That should be Fs, right? That should be Fs equal to 500 hertz. It's given in the question. Okay, now what will be this value? What will be this value? In the original signal spectrum, that value was 320. That was obtained by adding 320 from the mid band, right? Middle, I mean zero frequency, right? This length was 320. Similarly, what will be this frequency? You should add 320 from 500, right? From 500 you add 320, so you will get it as 820 hertz. So this is 820 hertz. Clear? Okay, similarly, what was this component? This component was actually it was 200. Okay, 200. So here it should be 500 plus 200. Here it should be 500 plus 200. That means 700. So 700 will be yet another. Okay, similarly here it is 500 minus 200, which is 300. Okay, and this value is 500 minus 320. Yes, 500 minus 320. What is 500 minus 320? It's 180. So this is 180. Actually, this 180 would come here. It may overlap, right? Actually, it should overlap because the sampling frequency or minimum frequency required to avoid aliasing, we have found out that it was Fs is equal to 640 hertz. Okay, but now the sampling frequency is only 500 hertz. Okay, so this is less than 640 hertz. That means there should be aliasing. Okay, anyway, so okay, now this is 2Fs. 2Fs means it is 1000 hertz, right? 1000 hertz. So this frequency will be 1000 plus 320. So 1320 hertz. This will be 1000 plus 200, 1200 hertz. This is 1000 minus 200 means 800 hertz. This is 1000 minus 320 hertz. That is 680 hertz. Okay, similarly negative values will be there, but they have asked to write some components. I mean, actually they have asked to what are the frequency components present in the output, but we know this will continue like this to the finite infinity, right? So there will be infinite number of frequency components. So what we can do is we can write only a few number of components. So starting from here, 200 hertz will be there, 320 hertz will be there, that is the original signal will be there. Then the next replica will be having 180 hertz, 300 hertz, 700 hertz, 820 hertz. Okay, next replica contains 680 hertz, 800 hertz, 1200 hertz, 1320 hertz, and so on. Okay, so that is the answer to this question. Okay, the next question is state and prove the time shifting property of Laplace transform. Okay, so first we'll see the statement of time shifting property of Laplace transform. The time shifting property says that if x of t is having a Laplace transform x of s, then the Laplace transform of a delayed version of the same signal x of t minus t0 will give a Laplace transform as e raised to minus st0 into capital X of s. Okay, so if you encounter a time shifting by t0 units in the frequency domain, you will experience a multiplication with the exponent. Okay, so let us prove this. So this was the statement. This is the statement. Now let us prove this. We don't know anything. All we know is just the definition of Laplace transform. So Laplace transform is given by integral minus infinity to infinity x of t e raised to minus st dt. This is all we know, the Laplace transform equation. Now what I have to do is, what I need is the Laplace transform of x of t minus t0 and not x of t0. So let me find out the Laplace transform of t minus t0. So L of x of t minus t0 as per definition is integral minus infinity to infinity. If the Laplace transform of x of t is to be found, then integral x of t into e raised to minus st dt. So if I have to find the Laplace transform of x of t minus t0, what change you have to make is you just replace x of t by x of t minus t0. Okay, so the Laplace transform of x of t minus t0 is x of t minus t0 into e raised to minus st dt. Okay, now let me do some steps, very simple steps. Let t minus t0 is some variable u. Okay, therefore what is dt? Dt equal to du, because t0 is a constant. It is a constant unit by which the signal is delayed. Okay, so dt is just du. Also from this equation, t minus t0 equal to u, what is t equal to t0 plus u. Okay, you can easily visualize these two equations. Okay, now let us continue with the integral. So this integral becomes integral minus infinity to plus infinity. What is x of t minus t0? I have put u as t minus t0, so I can write it as x of u into e raised to minus s into what is t? T is t0 plus u. So t0 plus u, and what is dt? Dt is tu. So du. Now what I do is just some rearrangements. X of u into e raised to minus st0 into e raised to minus su du. Is that right? I have just opened this bracket, so you will get this. Now what is e raised to minus st0? E raised to minus st0 is a constant. S is a frequency, complex frequency. It does not depend on time t, right? And t0 is, I have already told you, it is a constant value, a constant to which the signal is delayed. Okay, so I can take e raised to minus st0 outside the integral. That will give you e raised to minus st0 into integral minus infinity to infinity x of u e raised to minus su du. Now I can change the variable in the integral, no issue. So I am changing e raised to minus st0 into minus infinity to infinity integral. I am changing u to t. Okay, wherever you encounter, you make it t. So x of t into e raised to minus st dt. Replacing u by t, I will get this. So this is equal to e raised to minus st0 into what is in this bracket? This is nothing but x of s. Okay, so e raised to minus st0 into x of s is the Laplace transform of L of x of t minus t0. So hence the proof. Let's see the next problem. Find the inverse Laplace transform of x of s equal to minus 5s minus 7 divided by s plus 1, s minus 1, s plus 2 with ROC. That's the important part here. With ROC minus 1 less than RE of s less than 1. Okay, before starting the problem, let me have a slight intuition into the ROC part. ROC part specified in the problem. So, in Laplace transform, the ROC will be in the form of strip parallel to the y-axis. Okay, so minus 1, let me take the plus 1. So the ROC is given in the question, okay, given as the region between minus 1 and plus 1. So this is the ROC. Okay, I can write this is the ROC, region of convergence of the given Laplace transform. Okay, so in order to get such a Laplace transform, I'm giving you an intuition before starting the solution. So such a region of convergence will give you an intuition that one signal which is having a pole, one signal whose Laplace transform which is having a pole at minus 1 will be right-sided. Then only you can have a right-sided ROC from the pole. Okay, right to this pole, right? And the next thing I can say is another signal whose Laplace transform is having a pole at plus 1. That will be left-sided because the ROC from that pole is leftward. Okay, so I'm repeating these two impressions. This is very important. The signal having the Laplace transform with a pole minus 1 will be right-sided because the ROC is right-sided from the pole minus 1. Similarly, the signal whose Laplace transform is having a a pole at plus 1 will be left-sided because the ROC is seen left-sided from plus 1. Okay, now with that intuition, let me start solving the problem. Okay, so x of s is given by minus 5s minus 7. Whatever be in the numerator, you don't have to worry about. What we need to check is the denominator, s plus 1 into s minus 1 into s plus 2. To arrive at the inverse Laplace transform, what we do is you do the partial fraction expansion, and that will give you a by s plus 1 plus b by s minus 1 plus c by s plus 2. Okay, again you can adopt a simpler method to find out a, b and c. So I can write this as, this is equal to, what is a? A can be found out by finding which value of s brings 0 at the denominator. It is minus 1. Okay, so give minus 1 wherever s you find it in the main transfer function except at s plus 1. You just remove s plus 1. Okay, so a is equal to, put s equal to minus 1, right? To get a, put s equal to minus 1. So minus in the numerator you can see minus 5 into minus 1 minus 7. So minus 5 into minus 1 is plus 5 minus 7 divided by you have to remove this factor and put s equal to minus 1 in both other factors. So minus 1 is minus 2 into minus 1 plus 2 is 1. Okay, so this is minus 2 by minus 2 equal to plus 1. So a is plus 1. Similarly, let us find out b. So b can be found out by putting s equal to 1 for all factors except s minus 1. So what that will give you is b equal to minus 5 minus 7 divided by s equal to 1 means 2 into, you neglect this one, and then 1 plus 2 is 3. Okay, so this is minus 12 by 6, which is minus 2. So B is equal to minus 2. Okay, and finally what is C? C can be obtained by putting S is equal to minus 2 in the main transfer function. Okay, so put S equal to minus 2 and you will get as minus 5 into minus 2 is 10 minus 7 by minus 2 plus 1 is minus 1 into minus 2 minus 1 is minus 3. Okay, so this is 3 by 3 equal to 1. So finally C is 1. Okay, so this is our X of S. Now now we have to compare with the ROC intuition we have already had with the current Laplace transform. So the Laplace transform I've just got as having 3 poles, right? Obviously this is having 3 poles. One at S is equal to minus 1, right? So I'm marking S equal to minus 1 here, right? Another pole is at S equal to plus 1. Another pole is at S equal to plus 1. This is sigma or real part of S, and this is j omega, you know that. And the third one is having the pole at S is equal to minus 2. So here I can locate minus 2, right? And now we have to be very careful, be very attentive that the actual ROC is between minus 1 and plus 1. Okay, actual ROC is minus 1 and plus 1. And you know that if you have a term like this, multiple terms for this Laplace transform, then what is the final region of convergence? The region of convergence will be the common point or intersection of the region of convergence of the individual Laplace transforms. Okay, so you have to be very careful. So if you have to, if you need to get such an ROC, what we have to take care that the ROC, I'm talking about individual ROCs, the individual ROC for the pole minus 2, that means this term, okay, the individual ROC of that pole should be right sided. I can draw it like this roughly. Okay, I'm taking this term, so minus 2, from that minus 2 the ROC should be paka right sided. Okay, this should be the case. Okay, let it be there. Now I'm taking the next pole S equal to minus 1, so this term. Okay, so here it is minus 1. Now the ROC of this transform should be right to this pole like this. Okay, so what can you infer about the signal corresponding to this transform? It should be right sided. Okay, I can write it as the signal should be right sided because ROC is right to that pole. Okay, and similarly what was with this pole, this transfer function, that was also right sided because the ROC is right to its pole, its own pole. Okay, you consider its own pole minus 2 and ROC is right to that pole, so the signal corresponding to this transform will be also right sided. Okay, and finally we have one more pole which is at plus 1. You can see this, right? Plus 1, right? And if the ROC, if the ultimate ROC should be like this, how should be the ROC of this term? I mean this term, it should be left sided. Then only the common area, you can see the intersection of all the 3 colors is just this portion, right? So if the signal corresponding to this term is left sided, if at all it is left sided, we will get an ROC to the left side of that pole, and then only all the 3 intersection will give you this area as ROC. Okay, so I have written that the signal corresponding to this inverse transform is right sided, this one is left sided, and this is right sided. Okay, now we can boldly write the answer. Therefore x of t is equal to, what is the signal corresponding to the first term? It should be right sided, you know, so it is e raised to minus t u of t. Okay, and what is the signal corresponding to the last term? That should be also right sided, so it is plus e raised to minus 2t u of t. And finally, what about the middle term? The signal corresponding to this term should be left sided. Okay, so how can you write the signal? Actually, here it is a minus, so I have to invert it, plus. Okay, plus. Now 1 by s minus 1 corresponds to e raised to t, but this signal is left sided. To make it left sided, I have to multiply it with, not with u of t, but with u of minus t. Okay, so this is the answer. I have left a 2 here. It was 2 into e raised to, I have to add this 2, right? So 2 e raised to t into u of minus t. So this is the final answer.